The next layer on our agenda is the network layer, layer 3. But before we dive into the network layer, let's just make a couple of general remarks. When you have to study this work, I strongly suggest that you use mind maps, because on every layer you will find a couple of key concepts. On layer 4, we mentioned reliability as one of the key concepts. And then when we spoke about reliability, that naturally split into reliability prior to communication, during communication, and terminating the communication channel. In the case of the network layer, there are two primary concepts that you have to become familiar with. And that is routing. And if you want to route something, you need to talk about addresses. As we've just said, routing is one of the key concerns of the network layer. When one thinks about routing, you may think about something like an app that tells you how to get to a certain destination while driving along. In using that routing app or that navigation app, you will typically do two things. At some point, the route will be determined, and then you will typically follow the instructions. And what typically happens on layer 3 is that it follows the instructions. The determination of the route is something that happens elsewhere. It is an application layer protocol, layer 7 protocol. And we've briefly mentioned this when we discussed layer 7 protocols, but let's say a couple of things about those protocols. In the TCP/IP context, there are two protocols that determine routes that are really popular. And that's the Routing Information Protocol, RIP, and the Open Shortest Path First Protocol. The way these protocols work is as follows. Suppose you have a network, and then you want to add a couple of machines to that network. You would basically insert a computer between the two. That computer we may call a router. A router is just a computer that is able to route, so it doesn't have to be special, but sometimes it will look a little bit different and fit into a network cabinet and so on. And this router will typically have a couple of network interface cards, so it can connect to the computers in that network, and it has another interface, and it can connect to computers in that network. And then often, after you've done the initial configuration, it will simply work out, it will communicate with whatever other routers you may have in these other networks, and it will work out what the routes are that it needs to know about. So it may be as simple as plugging it in and simply using it. So the router that we've inserted there is typically known as an interior gateway protocol router. Internal, because it works within the organization. The two networks that we have there and there are assumed to be networks within the organization, and this interior gateway router simply communicates between the two. Now, at some point, this organization may connect possibly via a thick pipe to another organization or even to multiple organizations. And when you connect your organization to other organizations, then you will use an exterior gateway protocol. Exterior, You are going outside of your own network. And the best example of such a protocol is the Border Gateway Protocol. And that is a protocol that is nightmarishly hard to use, very hard to set up. If you make mistakes, you can literally break the internet. So there are very few people who know much about the Border Gateway Protocol. The interior gateway protocols, they will typically try and find the cheapest route based on some metric. And very often that metric will be the hop count, the number of routers it has to visit when it moves from the start of a message to the end of a message. In other words, if you want to send something from some machine A to some machine B, it will work out what is the lowest number of hops that you will use. In contrast, the Border Gateway Protocol may think about corporate agreements that you have. There may be corporate politics involved and so on. There may be legislation involved, exactly how you route traffic. So that's what makes it so hard to use that. One thing that I've just said for the sake of simplicity, I've said that I've talked about your company. And typically companies will not try and connect to one another. Companies will rather connect to ISPs. And this big ISP network will then connect to other ISP networks. So what we have here in what I deem to be a corporate or a company's network, that is really an autonomous system. And when we look up networks a little bit later in this video, you will see that the autonomous systems are identified, and the exterior gateway protocol is used to facilitate communication between autonomous systems rather than between companies. Now, recall that all of these protocols that we are talking about now are application layer protocols, layer 7 protocols. They determine routes. As we've said a moment or two ago, we will mostly focus on forwarding messages according to routes that have been predetermined. But it's important to take note of these protocols. These protocols are or use well-known routing algorithms that I assume you have encountered in previous modules. So the algorithms that protocols like RIP and OSPF will use are your typical algorithms like the Dijkstra algorithm, Dijkstra routing algorithm, Dijkstra, and the Bellman-Ford algorithm. So the algorithms are used in the routing protocols which operate on layer 7 and determine the routes. So let's look at an example of a network. What the routing protocols will do is they will typically complete a routing table at every node. So if we look at node B here, which we deem to be a router right now, it will complete a routing table that will essentially consist of two fields. And the two fields will be the destination and the next hop. So if in this first column I say we're routing here at B, so our destination will not really be B, let's forget about B, C, D, E, and F. The next hop is the next machine that the router should send a packet to if the destination is A or B or C. Now, in this example, what the routing algorithm will do is it will say, if you want to go send a message from B to A, just send it to A. It's plugged into one of your interfaces. Similarly, if you want to send a message to C, just send it to C. That network is connected via one of your physical interfaces. Similarly, if you want to send a message to D, then just simply send it to D. Same story. However, if you want to send a message from B to E, E is not directly connected, and here by inspection, because it's such a simple network, we know that we have to send the message to D. Similarly, if we want to send a message to F, the next hop on its path to F will also be D. So to stress what we've done here, we've completed a routing table, which a protocol that like RIP or OSPF or any other of those internal gateway protocols will complete. And we now know if some message arrives at router B and it is intended to go to A, how do we deal with it? We just look it up in the routing table and we send it on its way. There's a slight extension to this that we have to consider. It's possible that A and B and C and so on are not nodes, but they are networks, possibly local area networks, in which case you will deal with this in a very similar manner, where you will say if something has to go to something that is on network A, send it to the router A, which will then be able to deliver it. We will see this in more detail just now. Just to make this example slightly more interesting, if we were to connect those two nodes as well, then our routing table may look slightly different. Again, with our two columns, our destination A, and we're routing from B, so I'm not caring about that right now, C, D, E, and F. A will still be delivered or sent messages to A. It will still forward directly to A. Messages to C, it will still directly forward to C. Messages to D, it will still forward directly to D. But messages to E, if we look at the hop count as a metric, then going from B to A, that's one hop. Going to E, that's two hops. On the other hand, going to D and then going to E is also two hops. So there's no clear winner here, and the system basically has to make some random choice, and let's say it randomly chooses A. On the other hand, to go to F via this new link will mean that we go from B to A, to E, to D, to F. That is 1, 2, 3, 4 hops. But we can also go straight to D and to E, to F. That's only 2 hops. So this is clearly the cheaper option to go to D as our next hop. As we said earlier, the routing protocols such as RIP and OSPF are not the primary concern of Layer 3. We will be using a different approach and we will be using different examples. The primary example that we will use is the Internet Protocol, IP. And we will, over the next 4 videos, have quite a lot to say about IP. To give you examples that are not as common anymore, let's quickly mention 2 examples just so that you have a feeling for other protocols that may exist. One of the old routing protocols was known as used a technique that was known as bang addressing. So what you would do is, if you are here and you are connected to a couple of networks or a couple of computers, you are at computer A and you have them linked to B, C, and D, then you may say, take this message that I want to send, and I'm at A, so I can send it to B. And then I'm going to use an exclamation mark, which is read as bang. So the route to get to D, you would specify an email address like this, for example, B bang C bang D, and that gets you to D. Clearly that means you as a user have to remember the routes via the network, which is typically very hard to do. So what you as an organization would do is to remember a route to some very well-known machine. Let's call that a very important machine, NB1 or NB2, there could be many of them. And what you would do is remember the route to get to such an important machine. Now, if someone else is, for example, sitting on the network over here, let's say that's X, Y, and Z, they will advertise their email addresses or other addresses as how to get from well-known machines to their machine. So let's say this very important machine knows about X, and the computer Z will then advertise that to get to it, you can go from the very important machine to X, to Y, and to Z. So if I now want to send an email to a user on computer Z, I would simply take my little bit of the route that I know how to get from, so B, C, D, to this very important machine, and I will then take the published address that takes it from this very important machine, X, Y, Z, and then I will say bang, let's say it's user U. That's where the email should be delivered. Now, this was used in the very, very early days when people didn't really even think about the global network. It was known in the context of the UUCP, Unix to Unix copy systems. It wasn't used in the 1970s. No one uses bang addressing anymore. But here you can see how it is used. It is an example of source routing, where when you send out a packet, you tell it which route to follow. And we will encounter source routing again, even though we won't encounter bang addressing again. Our other example is still in use in quite a couple of places. It is the protocol that is used in ATM, asynchronous transfer mode. It's not anything to do with autobangs. This is a protocol that sends tiny packets of data, 48 bytes plus 5 bytes of header. It's 53 bytes, intended for use in multimedia context and so on, where you want a constant throughput. So telephone companies and those sort of companies would often support this. What makes it interesting is that initially, if you have a couple of nodes that need to talk to one another, you will send out a pathfinder packet. And that pathfinder packet will establish a path between these nodes, back and forth. And at every node, you will basically say, if something comes in via link 1, send it out via link 5. and then when it arrives at the next machine, at that machine's link 7, you will say send it out via link 1, and so on. That's the way you establish this path. So that's part of the route determination. And then the routing algorithm that really operates on layer 3 is at every node, when something comes in via a specific interface, specific channel, you just send it out via another specific interface, another channel. This is a sort of topic that we would have spent hours talking about only a year or 5 ago, but now we will leave it there and not explore it in more detail. As I said earlier, our primary example of a layer 3 protocol would be IP, the Internet Protocol. For many years, that meant only one thing. It meant version 4 that we nowadays would probably denote as IPv4, to be explicit. IPv4 has a couple of problems, and we will talk about them as we go along. I guess for the past 20 years or so, people have been saying that IP4 is broken, it will be replaced within the next 5 years, and clearly it has not happened. But it is happening right now. So the protocol that was designed to replace it was for a long time known as IP Next Generation. However, also many years ago, it was decided that that one would be numbered 6. So IP6 is the new IP protocol that is being deployed. It will still take years for it to take over the entire internet, but to see it actively being used, well, you can look at the internet right now. For those who are wondering, there was an experimental protocol, IP version 5, which was never used in practice, and that explains the jump from IP version 4 to IP version 6. We will talk about IP version 4 addresses in our next video.
Music